Have you ever just stopped and wondered how an AI like ChatGPT seems to, well, just get language? You type something in and it understands the nuance, the context, the meaning behind your words. It honestly feels like magic. But behind that magic is this really brilliant solution to one of AI's oldest, biggest challenges, understanding order. So let's dive into exactly how it works.
Okay, so check this out. We've got two sentences here. The dog chased the cat. The cat chased the dog. They use the exact same words, right? But they describe two completely different situations. I mean, one involves a pretty terrified cat, and the other, a pretty terrified dog. The only thing that changes is the order. Now, for us, that's super obvious. But for an AI, this is a massive problem it has to learn from the ground up.
And this really gets to the heart of the whole issue. To truly understand language, it's not enough for an AI to just know what words mean. It has to understand their sequence. It needs to know that dog coming before cat is fundamentally different from the other way around. Now, older AI models, these things called recurrent neural networks, or RNNs, they tried to handle this by reading a sentence one word at a time, kind of like we do. It worked, sure, but it was incredibly slow. Then in 2017, this game-changing paper called Attention is All You Need came out and introduced the transformer. Its superpower, it processes every single word in a sentence at the exact same time. This parallel processing made it lightning fast and, paved the way for the massive models we see today.
But wait a second, this created a huge paradox, right? If you're looking at all the words simultaneously, the model becomes kind of order blind. It just sees a jumble of words, not a structured sentence. So how do you give this incredibly fast, super powerful system a sense of sequence?
Well, the solution is this incredibly clever mathematical trick called positional encoding. Honestly, the best way to think about it is like this. If each word's meaning is a point on a map, positional encoding gives every single one of those words its own unique GPS coordinate. It tells the model exactly where that word is in the sentence.
So the key takeaway here is that positional encoding is just a system for injecting information about word order directly into the data the model sees. It's a way to explicitly tell the model, hey, this word is first, this one is second, this one is third, and so on.
Now, what's really cool is how elegantly they do this. So first, the model creates a bunch of numbers to represent a word's meaning. That's the token embedding. Then, it creates a separate bunch of numbers to represent its position. That's the positional encoding. And then it just adds them together. That's it. This creates a final enriched package of information that tells the AI both what a word is and where it is. The math behind it uses sine and cosine waves. Now, I know what you're thinking, but you really don't need to be a math whiz to get the big idea here. By using waves of different frequencies, this formula can generate a completely unique vector, like a digital fingerprint, for every single position in a sequence, no matter how long it gets.
And this is exactly why this method is so powerful. Because it's using sine and cosine, the values are always nicely contained between -1 and 1, which helps keep the training process stable. But more importantly, it gives the model a way to understand relative positions. It can start to learn things like what it means for two words to be, say, 4 positions apart in any given sentence.
So how did this clever little trick change everything? Well, this seemingly small technical fix, it didn't just solve a problem. It basically unlocked the entire modern era of AI. By solving the order problem, it allowed transformers to be scaled up to absolutely incredible sizes.
I mean, you can draw a direct line from that 2017 paper to the AI tools we're all using today. The transformer architecture, with positional encoding right at its core, became the foundation for every single major large language model that came after, from Google's BERT to OpenAI's GPT series all the way to ChatGPT.
And the scale we're talking about is just staggering. The original transformer had about 65 million parameters. Just 3 years later, GPT-3 had 175 times billion. This kind of explosive growth in size and capability was only possible because that parallel processing, which was enabled by solving the order problem, made training these absolute behemoths actually feasible. AI pioneer Andrew Ng really put it perfectly. The transformer wasn't just another step forward, it was a true paradigm shift. It completely redefined how machines process language and totally set the stage for everything that has happened since.
But, the story doesn't end there. As powerful as the transformer is, its core attention mechanism has a major scaling problem of its own. And of course, researchers are already hard at work on the next big breakthrough.
So here's the catch. This self-attention mechanism, where every word looks at every other word, has something called quadratic complexity. In simple terms, it means if you double the length of the text, the amount of computation required doesn't just double, it quadruples. This makes it insanely expensive to process really long documents, like a whole book or a big research paper.
So to solve this, a whole new field of research has popped up called efficient attention. The goal is to find clever ways to get the same results as that full attention mechanism, but without the massive computational cost. The two main approaches people are looking at are linear attention and sparse attention.
And this slide shows a great example called block sparse attention. Instead of every word looking at every other word in the entire sequence, which is total chaos, the model is forced to be more efficient. It only pays close attention to its immediate neighbors, what's called the local window, and then a few other pre-selected key blocks of text that are considered the most relevant. It's like getting most of the benefit with just a fraction of the work.
And this brings us to this final, pretty thrilling thought. This whole journey, from teaching an AI basic word order all the way to developing these hyper-efficient attention methods, it's all about expanding AI's ability to understand context. So the real question we're left with is this. What happens when an AI can process and understand an entire library of books with the same ease it now reads a single sentence? The answer to that? Well, that's going to define the next chapter of artificial intelligence.